Hello, this is the last recording for the course Formal Languages and Automated Theory. I am covering this just to complete, I would say, the understanding about Turing machines. So instead of, I would say, completing the syllabus is already completed. This is some extra topic which I think should be interesting. So we will compare Turing machines with our modern computers and we will see which one is better. Actually, we will show informally that both are equivalent under reasonable assumptions. So why informal? The first important problem that we face in this treatment is, what is really a modern computer? What do we call to be a computer, a modern computer? Actually, there is no standard, well-accepted definition, and the reasons are like this. There are modern computers available in a variety of shapes and sizes, like the most commonly used laptop computers or desktop computers. This is perhaps the most used thing. And then we will also talk about servers, clusters, graphic processing units, and so on. We will even have supercomputers. And if you add computer networks, all computers connected to a network may be considered as a huge computing device. And recently, there is some progress in the development of quantum computers, which are not quite like our classical computers. And there are other flavors also, like field programmable gate arrays, FPGAs, application-specific integrated circuits, ASICs, and so on. And also, your telephone, your washing machine, etc. Everything has some embedded processor. This is the Internet of Things. Anyway, so which one shall I consider as a modern computer? This is a difficult question. And on top of that, unlike Turing machines, the internal architecture of modern computers, even if it's a small processor like an embedded processor, the architectures are quite complex. And mathematically modeling them is a challenging task. Okay, so how to make a mathematical model of such a machine, a complicated machine of multiple varieties. Anyway, for this purpose, we will take a simple, very primitive laptop or desktop computer as a representative, and we will informally show that such a machine is equivalent in computing power to a Turing machine. Okay, so one by one in two directions. So first we will see how to simulate a Turing machine by a modern computer. So the input is some Turing machine M and an input W for M. I would like to write a C program to simulate the work of M on W. So M is specified by its that 7 tuple, 8 tuple, all this stuff. So how can I embed that information in a C program? It seems that this is no big deal. We can write a C program for that, right? But there are several issues to consider. It's not just being able to write a C code. There are several issues. First, a modern computer, like your laptop or desktop computer, has only a limited amount of memory. It's to be a huge amount of memory if you include hard disks and all that stuff. Maybe terabytes, even petabytes. But this is still a fixed amount of memory. But a Turing machine M, on the other hand, is gifted with an infinite tape. So it has an infinite amount of memory. So how can we simulate an infinite amount of memory in a limited space? So this is definitely an issue we have to solve. And then the description of the Turing machine, may be very, very huge. So huge that it does not fit in your finite computer's memory, modern computer's memory. If you include hard disk, everything, still maybe it's impossible to accommodate M. And likewise, W itself may be so large that it does not fit in computer's memory. Okay. There is no limit how large W can be, right? And also we may have this tape alphabet or input alphabet of M too large to handle. We are typically used to handle something like ASCII based 8-bit character sets, and we can also talk about 64-bit Unicode fonts for storing different symbols, but the tape alphabet may be much, much larger than that. Okay, so the important limitation of modern computers seems to be limited memory. And if you have only a fixed or finite amount of memory, a modern computer is no more powerful than just a finite automaton. But we have a solution for this finite memory problem. The solution is, we can assume we have an unlimited source of external memory like pen drives. Okay. So we'll use these pen drives, not a single one, but multiple ones, to simulate the tape of the Turing machine. And we assume that as many pen drives we want, or the simulation of the Turing machine wants, we can supply so many. Okay. And of course, for running this simulation, you may have to update your operating system, because you need some new type of file system in your pen drives and many other things. So let's not worry too much about that. So how to use a series of or a sequence of let's say pen drives, that is described in the next picture. So this simulation uses something like up to this point 0 to 8, that is 9 pen drives. The 6 is called the current pen drive. So the head is positioned somewhere in the memory location of this pen drive. Okay. And you write a code that reads some symbol from particular location of the pen drive, consult the transition table, move left or right after rewriting that old symbol. Problem comes when this head position wants to move out of this storage space in this current drive. If it wants to move left, of course, if this is 0 is inserted here, definitely it cannot go left, because the first symbol that you will get is the left end marker, left stop symbol. You cannot move past it. But if it is any other drive, then there is a possibility that the Turing machine's head wants to come to the left of the first position. If that happens, then you just take this out, put it here, and bring 5. Okay, the last cell of 5 will now be the location of the head. Okay, so these are all the pen drives that store the tape from beginning to the current position, and these are all the pen drives storing the content of the tape used up to this point. Of course, it cannot be infinitely many, up to this used part of the tape. Okay, and this is what follows this current drive. Both are organized as a stack. So this is the most recently used, this is the most recently used. Okay. Okay, fine. So this is one thing. So if you want to go to the left of the first position, you bring the top of the step from here, insert it and put it there. Okay. On the other hand, if the head wants to go out of the rightmost cell in this pen drive, you once again unmount it, put it here, bring the next one, and insert it here. Now what happens if this stack is empty? Then you have to open a new pen drive, the 9th one, okay, or the 10th one. So in words, this is something like this. Number the pen drives as 0, 1, 2, 3, and let's see the current pen drive in use. In that previous example, it was 6, C was 6, and the pen drives storing the part of the tape to the left of the current drive are organized as a stack. Likewise, the pen drive storing the used part of the tape to the right of the CH drive are organized as another stack. In each stack, we have the most recently used drive at the top. And if the head wants to move to the left of the first cell of the current drive, push the current drive to the right stack and pop and insert the drive at the top of the left stack. Likewise, if the head wants to move to the right of the last cell of the current drive, push the current drive to the left stack, pop and insert the drive at the top of the right stack. And if the right stack is empty, a new pen drive is opened with the next number. So by using a sequence of pen drives, we can have, theoretically at least, an infinite amount of memory capable of mimicking the work of the infinite tape of the original Turing machine M. So the infinite memory problem is therefore solved. The second problem, what if handling input or I would say tape alphabet, what if it is very, very huge? Okay. So, okay, input is fine. The input for M is now given to the pen drive, and therefore it can actually span across multiple pen drives. Okay, so even if it does not fit in your computer's storage, this is not a problem because the input can be broken down into multiple pen drives. And but if gamma is very large, this is a problem we have to address. The entire memory of a pen drive may be insufficient to store a single symbol. Okay. What does it mean? It means that for a 16 GB pen drive, we have this many bytes or bits. Okay. So, if the tape alphabet is bigger than even this quantity 2 power this is a gigantic quantity, but at least theoretically we may have a Turing machine whose tape alphabet is bigger than this. Then the problem is that some of the symbols will require more than these many bits. Okay. And if it is more than these many bits, the trouble is that you have to break somehow this symbol. One symbol you cannot break across multiple drives, right? So the solution is encode the symbols in binary. So now instead of calling the symbols as A, B, C, D, E, you are simply calling them as some sequence of bits. And then you can break a symbol across multiple pen drives. Okay. But then you add some extra overhead. What is that? You have to read. There should be a reading mode which keep on reading all the bits of an individual tape symbol, and then you have to interpret what symbol you have actually read. So that may actually increase the number of states of M quite significantly. Although the problem is now solved. The final problem we now need to solve is what if M itself is very, very huge. This problem also has a very cute solution. Input, no problem, it may span across multiple pen drives, but the description of M, this should be in the finite control of your machine, right? So M should reside in the internal memory of your computer, and M may be so huge that your internal memory is insufficient to accommodate the complete M. Okay, and the solution is very, very tricky. Instead of storing M, you just send M to the tape. Then how will that simulation go? You will, instead of loading M in your finite control, you load the universal Turing machine and let the universal Turing machine do the simulation job of M on W. So you simulate the universal Turing machine, you in turn will simulate M on W. Okay. So you simulate M on W, and the input for U is now M hash W, and this entire thing can now be given to the tape. And we are not worried about finiteness of the memory of your computer, internal memory of your computer. So you simulate M on W, and everything is now on the tape. Okay. But what about this U? U is a fixed machine, independent of any M or W. Okay. And you can convince yourself that U has a moderate size. Okay. It is not a machine which is very, very big. It is a moderate size and is independent of M and W. Okay. So you just use enough memory in your internal memory of your computer to accommodate U and nothing else. Okay. M and W may completely be transferred to the tape. So one by one we handle all the problems associated with the simulation of a Turing machine by a modern computer. Now the next question is, what about the converse? Okay. The converse seems to be a bit more, I would say, informal, because now a Turing machine, which we know very, very, I would say, clearly and mathematically, is going to simulate something which does not have a very good mathematical description. But in any case, we will make some assumptions about our modern computers and see how a Turing machine can still simulate the working of a modern computer. So, current-day computers are called stored program computers, invented in early 1950s, something like that. So, nowadays, of course, we have to understand what is meant by stored program. So, programs essentially reside in the memory. And in a modern computer, memory is organized into several, I would say, levels. Registers are the fastest one, which essentially reside in the CPU. On top of that, you have several levels of cache memory. Then you have your RAM, read-write memory, main memory, and you have hard drives. And modern computers also support removable storage like pen drive. So, because we have this removable storage, which can be assumed to be available in any amount as we desire, we assume that the memory of a modern computer is infinite. Okay. However, we will not worry too much about which type of memory we are dealing with. So we will simply flatten this hierarchy. So memory means memory, whether a register, it's memory, whether it's in cache, it's also memory, main memory, hard drive, removable storage, whatever is this, we call it a memory. We flatten this hierarchy because these memories essentially differ only by their access times. With access fastest here, possibly slowest here, and whatever memory access, this difference of these between these access times are, they are after all constant factors. So we will not worry about what kind of memory we are dealing with. Instead, we will assume that this memory is organized as an array of words. A typical today's machine, we have 64-bit words. Slightly older machines, we have 32-bit words. Of course, for the purpose of the simulation, it's not a very, I would say, necessity to assume that a word is of fixed length. But even if we assume this, there is no harm. And these words, this is actually not a finite array, this is an infinite array, and we will give them addresses 0, 1, 2, 3 and so on. Okay. And when you compile a program, you get something like a.out or some exe file. It resides somewhere in this same memory. Okay. Now, this compiled program is a sequence of instructions. Okay. And instructions are typically of this type. Here are some examples. Copy the content of the ith word to the jth word. This is a copy information instruction. Add two words, the contents wi and wj, and store the result in location k as word k, wk. So this is typical arithmetic operation, this is copy operation, this is a comparison operation, and compare wi with wj, maybe for equality greater than or equality less than equality and something like that. And I also have jump addresses, jump instructions, jump to some given address L. Okay. Whatever it is, your architecture supports a set of such machine instructions. These are called assembly instructions, and each machine has a different set of assembly instructions, depends on the processor. But what is important is that the number of assembly instructions that each machine can provide is finite. Okay. You cannot have an infinite number of assembly instructions, basic instructions like this. And what about the input? It may be stored in the memory itself, or it may come from a special device like your keyboard. Okay. And then when we have a sequence of such instructions, how does your modern computer actually execute it? This is what is called the fetch, decode, execute cycle. Okay. So each instruction, as we have seen many examples, consists of three parts. Part 1, an opcode. This is the assembly instruction. What operation is being meant. This is followed by one or more or zero or more operands on which you apply the operation. And the third is the destination address. Okay. Of course, in some, I would say, operations, some of these things are not present. Of course, opcode has to be there, but some operations do not require operands. Some operations do not require destination. Anyway, this is how each instruction looks like. Okay. And a counter, this is often called the program counter. This stores the address of the instruction to execute next. At the beginning, it is the first instruction that the counter or the address of the first instruction in your code, in your compiled code, that the program counter or the instruction address counter stores. Then what happens? From the current address of the instruction, the opcode is fetched and it is decoded. So you, depending upon the opcode, you know what other things you also want. And if this operation requires some operands, they are one by one fetched from memory, and then the operation is performed and the result is written back to the destination address. This is how each instruction in a modern computer is typically handled. But this essentially talks about arithmetic instructions or logical instruction or even comparisons. You may also talk about jump instructions. If the instruction is a jump instruction, the instruction address counter, whatever it is pointing to, this is rewritten by this jump address. Okay, the operand. So jump to this location. So otherwise, okay, jump to this location. So your instruction, this program counter will now be rewritten by this new address, jump address. Otherwise, you have to go to the next instruction. So you increment that counter to go to the address of the next instruction. So this is the typical fetch, decode, execute cycle that almost all computers, all of today's computers keep on doing. Okay, and finally, initially the counter is loaded with the first address of the first instruction. So somehow the Turing machine will have to simulate the working of this and the infinite memory of the modern computer as we have mentioned. So this is done this way. We will use something like a 6-step Turing machine. The first step will store the memory of the computer as follows in this organization. So left-hand marker, address 0 followed by a marker, the content of word 0, followed by another marker or another separator, hash, then 1. 1 means location 1, star, separator, the content of word 1, and so on. So each W0, W1, W2, Wi is the content of the word at address I. Both I and Wi are encoded and stored in binary in this fashion. So the memory of the computer can be stored in this fashion. Then what about the remaining 5 steps? The second step will store this program counter or the instruction address from where to fetch the next instruction. And the third step will be used to store the operand addresses. Operands are needed for some instructions. These addresses will be stored here. And let us say we have a scratch tape for doing all calculations. This is the 4th step. This is used for all operations. Okay. And the 5th step is where the input is provided. And the 6th step may be used to write the outputs meant for the user. Okay. And the finite control stores the instruction set, the complete instruction set of the computer, that is all opcodes and their meanings, what to do with each opcode. Okay. So this machine looks like this. Finite control, it stores all the information about the assembly instructions of your computer. The memory is organized like this: 0, W01, W1, 10, W2, 11, W3, and so on. This is the instruction address. This is the address from where you will fetch the next instruction. And this is maybe the 2 operands are needed. One is at address this, another one is at address this. So something like this. And this is needed for the calculations. And then input is read from here and output, if needed, supplied to the user in the 6th or last step. Okay. So how does it work then? How does it, I would say, execute or simulate an instruction cycle of a modern computer? So from the second step, you have an address. So make a linear scan over the first step to locate the word with that address. Okay. Locate that address. For example, if address is 5, you have to go 0, no, 1, no, 10, 11, and then 100, no, 101. Okay. Now there is a match, and then you bring that instruction W5. Okay. Read that and remember that opcode is the finite control. You don't have to store it anywhere. The finite control knows what to do with that kind of operation. In particular, it knows whether it requires further operands. If so, the operands will be part of the instruction, maybe written as W6, W7, something like that. So copy the operand addresses, if needed of course, from the rest of the instruction to the third step. And then you bring the actual values of the operands one by one from the memory by scanning the entire memory. Okay, look at the operand addresses of the first step and copy the operands to the fourth step. So now everything is ready. Fetch, decode, execute, fetch and decode are done. Execute is actually the easier part. Apply the operation on the operands of the fourth step. So we have seen in the class several examples like addition, multiplication, all these things can be done in binary or unary. Okay. So this, I would say, rough work is done on the fourth step, and then the result is produced also, the result is produced in the fourth step itself. And then we look at the destination address. Once again, this is part of the instruction. Look at the destination address and copy the result to that destination address. And if that destination address is not big enough to accommodate the result, you may relocate the rest of the tape. However, if we assume that we use fixed word lengths and the results are of fixed size, then this relocation is not necessary. And if it is a jump instruction, then replace the second tape by the content of the third tape. Okay, the jump instruction contains the address where the next address from where the instruction has to be fetched. So the second tape contains that instruction address. This is overwritten by the third tape. Otherwise, you simply increment the second tape by an appropriate amount, such in order to skip the opcode and all operands, destination address and all that stuff. Okay. So that's it. If one cycle in the fetch, decode, execute kind of work of a modern computer can be simulated by a Turing machine, then whatever the machine can do can also be simulated. Okay. Now one thing I will very informally describe. Okay. Before that, let us see. This is once again not a very important question, but input and output can also be handled by this simulation. So actually, input and output are not exactly parts of the computation. And we assume that there are specific read or write instructions for your machine's architecture. A read instruction scans the input from specified addresses on the fifth tape. Okay. You may specify some address, read from this place, or you may one by one keep on reading. Okay. And this fifth step is the input step. Likewise, a write instruction prints the output to the specified addresses of the sixth step or sequentially. Okay. And there are special drivers that handle this input and output. And there are peripheral devices that handle this step. For example, a keyboard controller can write to the fifth step. Likewise, a screen controller can read from the sixth step in order to change the graphic display. Okay. In addition to this input and output, the Turing machine may have an accept state and a reject state, T and R. If the program successfully halts, then M goes to T and halts. If the program unsuccessfully halts or terminates, M goes to R and halts. Now this question of successful or unsuccessful termination is very much context dependent. It may be exit 0 is successful, exit anything non-zero may be unsuccessful, whatever. Okay, so now what about the running time of the simulation? This is an important question. Apparently, this Turing machine's head will have to move back and forth many times. And does it actually affect the running time? Definitely it does, but not too much. Okay. Suppose that some program takes n steps in your computer. Then we make certain assumptions. We may assume that words are of fixed size like 64 bits, and overflows during arithmetic operations are ignored. So all results are 64 bits. And then it is calculated in a book that this simulation of this n-step computation by the Turing machine can be done in big O of n cube steps, individual steps of the Turing machine. And in particular, this is a 6-step machine. If you have a 1-step machine to do this task, the simulation time becomes big O of n power 6. So this has one important implication. If n is a polynomial in the input size, n power 3 or n power 6, they are also polynomials in the input size, of course of higher degrees. But this is very important because this implies two very important results. The notion of polynomial time computability is quite robust, and second, we can use the Turing machine to address the question of polynomial time computability. So it's perfectly capable of capturing the notion of polynomial time computability. Fine. So this is a very brief and overall description of these two simulations, and as this is not really a part of your syllabus, no tutorial exercises this time. However, if you choose, you may informally argue how a Turing machine can simulate a C program instead of its compiled version. You just want to, that Turing machine will have to, if given a C program, it will execute it. Okay, in the intended fashion. So in particular, you have to handle variable names, function calls, dynamic memory allocation, and all that stuff. All this can be done. You may assume multiple tapes for the Turing machine. Each tape is infinite, and it can, for example, one tape can be used to implement the recursion stack, another for dynamic memory allocation, and so on. In any case, it is doable. Essentially, you have to write a C compiler for Turing machines. Okay, so don't do that, but just mentally argue that this is also possible. Okay, so here I stop. This is the last online video from me. So see you when you have a chance. Bye. Take care.